Hello, everybody. Welcome back to Learning as a Hobby. I apologize for uh, not making a video for the last week and a half or so. Um, First, we started off with the holidays, so I took a couple days off for that, and then unfortunately, my wife and I ended up getting COVID. We're feeling better now, but I didn't feel up to making videos until today, so I want to continue with the solutions to Spivak today, chapter 3. And I think because the problems are kind of long, I'm going to split this into the exercise solutions into two videos. So we'll do part 1 and part 2. Um, and today sorry, in this video, we'll look at the solutions for half of the problems, and we'll look at the other ones in a separate video that if I feel up to it, I'll do the second video today as well. If not, then I'll do it tomorrow. So let's bring up the solutions that I wrote up. I do apologize for my voice. I still have a bit of a gravel to it. Um, there's nothing obviously that I can do about it, but hopefully it's not too difficult to understand what I'm saying. All right. So these are the problems that I chose to do for um, chapter 3 in Spivak. He doesn't, in the chapter itself, he doesn't mention which problems that you should do in the exercises. So I just chose ones that either looked important to me or looked interesting. In this first video, part 1 of the solutions, I'm going to go over these problems here. And then in the second video, I'll do these 3 problems in number 20. So, like I said, that each of them have like a bunch of parts to them, and they're kind of long. So that's what we're going to do today. So before I repeat myself another time, let's actually get to the problems. So let's start with number 6. Number 6 is the derivation of what's called the Lagrange interpolation, which is an important concept. So I wanted to do that one, and it's done in 2 parts here. So question 6, part A says if x1 through xn are distinct numbers, find a polynomial function fi of degree n minus 1, which is 1 at xi and 0 at xj for j not I. All right, and let's erase these things. This is basically the function that the way you define the y coordinate for the function. So fi of x is equal to I don't know if you guys are familiar with this this symbol here. It's sort of like similar to the summation symbol, like the sigma notation, but it's for products. So it's sort of like a giant pi symbol, and it means product. So just if you haven't seen this before, just so you can see how it's used, if I want to take the product j going from 1 to 5 of j, let's say, this would be equal to 1 times 2 times 3 times 4 times 5. Right, so it's sort of, like I said, it's sort of like the summation symbol, the sigma notation, but it's for products instead of sums. All right, so this is the way we're defining that polynomial. And let me do a specific example because it might be confusing looking at it written that way. Let's say that we have 3 numbers. Let's do 1, 2, and 3. And say I want to write down the function f sub 2 of x. Using the definition here, that would be equal to x minus 1 times x minus 3 divided by 2 minus 1 times 2 minus 3, which is negative x minus 1 times x minus 3 when you simplify. And notice if you plug in if you plug in 1 in for x, you get 0. If you plug in 3 in for x, you get 0. And if you plug 2 in for x, you get minus 1 times minus 1, which is 1. So all the conditions are satisfied. And this is the general form that you need for those polynomials. All right. So let's take a look at part B then. In part B, we're going to use what we just derived in part A. to write down the interpolation formula. Right, so in part B, now find a polynomial function f of degree n minus 1 such that f of xi is ai, where a1 through an are given numbers. Right, so again, if we have that family of polynomial functions that we defined in part A, we define the function f of x, the y value for the function f to be f of x equals this. So you just take the sum of the ai's times the fi's evaluated at x, and that gives you exactly what you need. Right, so that's called the Lagrange interpolation. All right, that's question 6, part A and B. 7a says, prove that for any polynomial function f and any number a, there's a polynomial function g such that f of x is x minus a times g of x plus b for all x. Or in other words, you can, if you have a polynomial of degree greater than or equal to 1, you can divide by a polynomial of lesser degree. So here's the proof. It's by induction on the degree of the polynomial, which is n. The base step, if the polynomial is linear, so the degree of f is 1, then f of x looks like bx plus c for some constants b and c. And if you notice, you can rewrite that as x minus a times b plus c plus ab. And that means that g of x is this constant function, and the constant b is this number here. All right, so the base step is satisfied. All right, inductive step says assume that you always start with the inductive hypothesis, right? Assume the proposition holds for any polynomial f of degree n for some n a natural number. Consider a polynomial f of degree n plus 1. And then you just do your long division of polynomials, if you remember back to pre-calculus. So f of x, if it has degree n plus 1, it looks something like this, right? Divide by x minus a, and you get this quotient on top, and when you subtract, you end up with some function g of x, some polynomial g of x, where the degree of g, this should be degree of g of x is is n, okay? And using our inductive hypothesis, that means that g of x can be written in this form: x minus a times h of x plus c, where h of x has degree less than g of x. Right, and then just rearranging things, you get what you want. So f of x has to be x minus a times an plus 1 times x to the n plus h of x, and then plus your constant c. All right, so that shows that you can do that for any polynomial. All right, part B, prove that if f of a is 0, then f of x equals x minus a times g of x for some polynomial function g. And he says in the book the converse is obvious. If it's not obvious to you, you would start with this. And if you plug in a in for x, clearly you get 0. So the converse is straightforward. So he wants us to prove the forward direction of the biconditional. All right, so here instead we'll assume that f of a is 0. Then using part A, 0 is f of a equals 0 times g of a plus c, which means that c has to be 0. So that means that f of x equals x minus a times g of x. That follows directly from part A. All right, part C says prove that if f is a polynomial function of degree n, then f has at most n roots. This one I think I did by contradiction. Let f be a polynomial degree of let f be a polynomial of degree n, for a natural number n, assume for the sake of contradiction that f has roots a1, a2 up to ak, where k is greater than n. By part B, we know that f of x is x minus a1 times g of x, where the degree of g is n minus 1. And also assuming that here, if a1 equals a2, you still get similar factorization, you just get an extra factor of x minus a1. So assuming that it's not, then you get that g of a2 has to be 0. So that means that f of x is x minus a1 times x minus a2 times some polynomial h of x, where degree of h is n minus 2, and you keep going on like that. And assuming that the polynomial has k roots, that means that you can factor f of x until it becomes just a product of these linear factors, x minus a1 times x minus a2 dot 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 all the way to x minus ak. However, if k is greater than n, that means that f of x has degree greater than n, which is a contradiction because we assume that the degree of the polynomial f was n, and that shows that f has to have at most n distinct roots. Right. Part D, show for each n there's a polynomial function of degree n with n roots. If n is even, find a polynomial function of degree n with no roots. If n is odd, find one with only one root. So you just come up with some examples, which is what I did. So for example, a polynomial with exactly n roots looks like this. Right? Or distinct. I guess it doesn't have to be distinct. Did he say distinct? Whoops. Show that for each n, there's a polynomial function of degree n with n roots. So here, this is the polynomial that I picked. Again, if you're not familiar with that product notation, all this means is x minus 1 times x minus 2 all the way up to x minus n. So clearly that polynomial has n roots, right? He didn't say they have to be distinct, but that's the one I picked, and it has distinct roots. F of x equals 1 has degree 0, which is even, and it also has no roots, which satisfies the conditions that he wanted. And f of x equals x minus 1 has degree 1, which is odd, and has one root. So those are the examples that he asked for. Right. 3.8. For which numbers a, b, c, and d will the function f of x equals ax plus b over cx plus d satisfy f of x equals x? All right. Here's the solution. So if you evaluate if you take f evaluated at f of x, you get this complex fraction, and then when you simplify, you get this rational expression here. And if you want that to be equal to x, then you get some conditions on the variables, which gives you this system of equations. For example, you would need this to be 0, you would need this to be 0, and you would need this to be equal to this. And if you use those conditions, you get the system of equations that I have written here. All right, and then using those conditions, we get that either from the third equation, either a is d or a is minus d. And from the first two, you get either b is 0 or a is minus d, c is 0 or a is minus d, and so on. So there's two things to consider. First, either a plus d is 0 or a minus d equals 0. All right, so first I assume, well, I'm doing this in cases here. If a plus d is 0, then if you plug that into the rational expression that we have above, then you get this, which is equal to x for all values of a, b, and c, provided that a squared plus b squared is not 0, because again, division by 0 is not allowed. All right, case 2, a minus d is equal to 0, and by the first two equations in the system, that implies that b has to be equal to 0 and c has to be equal to 0. So again, plugging those conditions in, we get this has to be true. AX over A has to be X, and these will always cancel provided that A is not 0, right? So if this is true, then it's okay as long as A is not 0. And case number 3 is when A equals D equals 0. And when you do that and simplify, you get this expression here, B over CX. Obviously, this is defined for all X not 0 because division by 0 is not allowed. And this is defined for all values of B and C, provided that C is not 0. So those are all that exhausts all the cases. All right, 3.9 there's a few parts to this as well. Part A says if A is any set of real numbers, define a function C sub A as follows. And erase that part. This is sometimes called the indicator function for the set A. He doesn't use that term here, but you might hear it referred to as an indicator function. So the definition of C sub A of X is it's equal to 1 when X is in the set A, and it's equal to 0 when X is not in the set A. And so in other words, it indicates when the input value is an element of the set A by outputting a 1. All right, so find expressions for C intersect, sorry. Find expressions for the indicator of A intersect B, the indicator of A union B, and the indicator of A complement in R in terms of the indicator of A and the indicator of B. All right, so you just work it out. This is what you end up with. Just to show you that it works. For example, in this first part here, if you want the indicator of A intersect B, you take the product of the indicator functions for A and B. So for example, if X is an element of A intersect B and Y is not an element of A intersect B, then you get, so if we evaluate this at X, using the definition that we just made, this is defined to be CA of X times CA of B. Sorry, I'm sorry, CB of X. Right. And since A is in the intersection of A and B, CA of X is 1, CB of X is 1, so you get 1. And if we evaluate CA of, the indicator of A intersect B of the value of Y, that's again defined like this. Right, and at least one of these factors in the product is 0 because Y is not an element of the intersection, meaning it's not in both A and B. So this one of these factors will have to be 0, or both could be 0, which means that you get 0. Right, so that works for the indicator of A intersect B, and you could check these other ones that I defined here similarly. Right, so the indicator of A union B is given by C of the indicator of A plus indicator B minus indicator A times indicator B. And the indicator of the complement of A with respect to the real numbers is 1 minus the indicator of A. So you could check those yourself and you'll see that they work. All right, so that's the answer for that part. I think there was at least one more part to this. All right, let me scroll down. All right, part B, suppose f is a function such that f of x equals 0 or f of x equals 1 for each x. Prove that there is a set A such that f is the indicator of A. All right, so here's my proof. Let A be a subset of the domain of f such that A is all the elements of the domain of f for which f of x equals 1. Then f is the indicator of that set A. That's basically it. Part C, show that if f equals f squared, show that f equals f squared if and only if f is the indicator for A for some set A. Oh, I just realized I only did one direction of this. Let's look at this first. Let x be the element. Sorry, let x be an element of the domain of f. Then f of x is f of x squared. By the definition here. And then subtract f of x from both sides. And when you factor, you get f of x times f of x minus 1 equals 0. And that means that either f of x is 0 or f of x is 1. So that is that means that f is an indicator for some set. And then let's see, it looks like I forgot to do the reverse direction here. So the reverse direction would be let f be the indicator for some set A, and we want to show that f equals f squared. Actually, that part is relatively straightforward because f can either be 1 or 0, and the square of both of those numbers is itself. So actually, maybe it's all right if I skip that direction, right? Because, for example, if f of x is 1, I mean, that's equal to x1 squared, right? So that's equal to f of x squared. And so on. Same thing for 0, right? So I'll just skip that, writing that down. I didn't mean to skip it in the notes, but all right, 313. Prove, so there's two parts to this one as well. Prove that any function f with domain R can be written f equals e plus o, where e is an even function and o is an odd function. So here, if you fiddle around a little bit, you'll see that these two functions work. So the even function you can define as f of x plus f of minus x over 2, and o of x is f of x minus f of minus x over 2. You can test that both of these are, one of them is even, one of them is odd. For example, if you take e of minus x, this is f of minus x plus f of minus x over 2. And if you simplify that, notice you get f of x minus plus f of minus x over 2. And you can check that O is odd by, doing a similar test. And if you add those two things together, notice that you get f of x. So that's what I'm doing over here. So notice that since I didn't pick a specific function f, this works for any function. So that shows that this is true. All right, part B, prove that this way of writing f is unique. Right, so the way that we do that is we assume that it isn't, or assume that you have two other functions that are that have the similar property. So f is e plus o, and that's the same thing as e prime plus o prime. Okay, and then if you just, for example, subtract e prime from both sides and subtract o from both sides, you end up with e minus e prime equals o prime minus o. And the difference of even functions is even, the difference of odd functions is odd. And that means that this is equal to the function that is identically 0, meaning that it's 0 for all values of x. And that means that E has to be E prime and O has to be O prime. So the way of writing f as a sum of an even and odd function is unique. Right, and then last one for this video, 314. If f is any function, define a new function, absolute value f, by absolute value f of x equals the absolute value of f of x. If f and g are functions, define two new functions, max fg and min fg, by this way. So max fg of x is the maximum of f of x and g of x. The minimum of fg of x is equal to the minimum of the y values here, f of x, g of x. And they want you to find an expression for those things in terms of the absolute value. And in order to do that, you have to use a lemma from chapter 1. The exercises of chapter 1. It's actually exercise 113, which is one of the problems that I didn't actually do on video. So I'm doing it here, or at least part of it. I'm doing here the part that we'll need. This is the lemma. So xy, let xy be real numbers. Then you can define the maximum of the two numbers using this formula in terms of absolute value. And you can define the minimum this way as well. I proved the lemma over here. So it's by cases. If x is greater than y, then the absolute value of y minus x is the same thing as negative y minus x without the absolute value. And if you notice, when you cancel, you get x, which is greater than y, so that's the maximum. Same thing if y is greater than x, and same thing for the same thing for the minimum of x and y, using the same idea with the expression here. If y is greater than x, then the proof is similar, so I won't write that out here. And then I basically just use that lemma to prove the problem, to prove the statement in the problem. So define this function this way, and using that lemma, you can write it like that. And same thing for the minimum, you could write it like that, just literally using that lemma. Right. Oh, is that it? I thought there was multiple parts to that one, but I guess there isn't. Okay, well, that's problem 6. Which ones did I do? 6, 7, 8, 9, 13, 14. I'll make a separate video for problems 15, 16, 17, 20. So I should be able to finish those up relatively soon. But I'll end this video here. I hope that my voice wasn't too bad and that you guys were able to understand what I was saying and that I didn't go too fast. But, leave me comments in the comment section and let me know. So I'll post the second video relatively soon. Keep an eye out for that. And I also have Spivak, I also have Schifrin section 1.4, I think it is, 1.3 or 1.4, I forget off the top of my head. I have that the notes for that coming up soon and the exercises. So should be posted within all of those videos should be posted within the next couple of days. All right, guys, so I'll see you in the next one.